Hi everyone, my name is Alyssa. I'm a third year student from International Program in Artificial Intelligence Isho University. And now I'm gonna present to you my embedded system final project, Secure Information Lock. So for today's agenda, I'll be telling you about the platform designer structure, the design flow of my code, the real-world application, and the lesson I learned from this project. The Secure Information Lock project is designed as a demonstration of a secure system that restricts access to confidential information until a correct password is entered. The lock secures two types of personal information: the last 6 digits of a student ID and a birthday. The system ensures that unauthorized users cannot access the information unless they provide the correct passcode. Once the correct passcode is entered, the confidential information becomes visible through a switch mechanism. This project utilizes FPGA hardware and the platform designer to create an efficient and secure implementation of the lock. The primary purpose of this project is to create a secure information storage and retrieval system. The objectives are as follows. First, to protect sensitive information. The project aims to securely store sensitive information, such as my last 6 digits of the student ID and my birthday, ensuring it is not accessible without the correct passcode. Second, to demonstrate practical application of FPGA. This project highlights the potential of FPGA-based system in implementing secure solutions for data protection through effective hardware-software integration. Third, to develop user interaction mechanisms. By incorporating switches and LEDs, the system allows users to interact with and retrieve information securely and intuitively. Fourth, to provide educational value. The project serves as a learning tool for understanding secure system design, C programming, and the use of platform designer for hardware development. The platform design structure is a fundamental part of this project as it defines the hardware components and their interconnections within the FPGA. Now let me tell you the detailed explanation of the structures and its significance. First, it's going to be the clock sources and distribution, and then the processor, on-chip memory, SD-RAM, peripheral interfaces, and then the address map. So first, the clock sources and distribution, the CLK0. This is the primary clock source in the system. It is connected to multiple components like NEOS to Gen 2 0, on-chip memory to 0, SD-RAM, ensuring synchronous operation across the platform. The clock source is listed as exported, allowing external hardware to provide the clock signal. And then the PLL outputs, PLL0 out CLK0, and also the PLL0 out CLK1. These outputs are generated by a phase lock loop, or PLL, to provide additional clock signals with different frequencies or phases for various subsystems such as SD-RAM and peripherals. Second, the processor, which is NEOS to soft processor, NEOS to Gen 2 0. This is the main processing unit, NEOS to soft processor, responsible for executing software programs. So the key connections are: instruction master connects to memory or instruction storage to fetch program instructions. The data master accesses data memory for reading or writing. The IRQ, interrupt receiver, handles interrupts from peripherals. Debug signals, interfaces for debugging and reset management. And then we have on-chip memory, which is the on-chip memory 2.0. It provides on-chip storage for program instructions, data, or stacked memory. It is connected to the NEOS 2 processor via Avalon Memory Map (MM) interfaces. For the features, there are clock input and reset signal. The clock input operates synchronously with the primary clock, and the reset signal ensures proper initialization on system reset. Next is the SD-RAM. The off-chip dynamic memory used for larger data storage or program memory. It is connected to the NEOS 2 processor via an Avalon memory mapped slave interface. It operates with a dedicated clock, which is SDRAM underscore CLK, typically derived from the PLL. Next, it's the peripheral interfaces, the PIO, parallel I/O components. There are switches. It reads input from hardware switches and passes the state to the NEOS 2 processor. External connection provides the physical connection to the switches. Next is the control and LED HEX 89. Similar PIO modules for additional external connections or interfaces. Second one is the JTAG UART. It enables communication between the system and host PC for debugging or data transfer using the JTAG interface. It is connected to the NEOS 2 processor for console I/O during program execution. Then next is timers, which is the timer 1 and then the timer 2. Interval timers configured to generate interrupts at regular intervals. It is useful for scheduling tasks or triggering periodic events in the application. And then last is the address map. The base and end columns in the images define the memory address ranges allocated to each component. On-chip memory to 0 is mapped from 0 times 040402000 to 0 times 0404003FFF. These addresses are critical for software to access the components. Now let me tell you the design flow of my C code. The C code is the software backbone of the Secure Information Log project. It implements the logic needed to ensure data, security, and user interaction. Below is a detailed explanation of its design flow. First is the passcode verification. The main functionality of the system is to verify a user's input against a randomly generated log pattern. We have input mechanism. The user inputs a 4-bit passcode using hardware switches, using the SW0, SW1, 2, and 3, and then the passcode matching. A random 4-bit log pattern is generated from a predefined set of patterns using pseudo-random number generator seeded with the initial state of switches and runtime variability. And for the user input is continuously read and compared with the generated log pattern. If the input is correct and it matches the log pattern, the system unlocks and provides feedbacks by turning on all the LEDs. The user is then allowed to access the sensitive information, which is my student ID and my birthday. But for the incorrect input, if the user input does not match the log pattern, an incorrect message will be displayed, and the LEDs reflect the current input. Okay, now second, information display. After successfully unlocking the system, the user can choose to view sensitive information. For the switch-based selection are SW6 and SW7. For SW6, display the student ID on the HEX display. It will only display my last 6 digits of my student ID. And for the switch 7, it displays the user's birthday, which is January 17, 2004, on the HEX display. This ensures that sensitive information is shown only upon explicit user request, reducing accidental exposure. Third, security mechanisms. While basic, the code includes some security-focused elements, which are 1. Randomized log pattern. The passcode is chosen randomly from a predefined set, adding a variability to the system. Second, LED feedback. LEDs visually indicate the user's input or the success or failure of the verification process. And then third, limited input space. The use of 4-bit patterns inherently limits brute force attempts. Through further measures like a lockout mechanism could enhance security. And then fourth, user interface. The system provides a simple and intuitive user interface through hardware components. Like switches, I use the switch 0 until 3 and switch 6 and 7. They are used for passcode input and to select the desired information to be displayed after unlock. Next, I also use the LEDs. It indicates the current system status or reflect user input. I also use the HEX display. It displays either the student ID or birthday upon user's request. Hello everyone, so I'm making a secure information lock. So let's run it together. So actually I have two information here that we can see if we toggle the switch 6 and switch 7. But because we haven't opened the lock yet, we cannot see the information. Right, look. So we need to guess the passcode first because the code generate a random passcode and we need to guess. Let's try. If the passcode the switch I toggled is correct, all of the LED here will be turned on. Oh, it's turned on because the passcode the switch I toggled is correct. Now, I can try the switch 6 and switch 7 because it's already open. Let's try switch 6. It will show the last 6 digits of my student ID. And now let's try the switch 7. Now it's my birthday, January 17, 2004. And it's also shown here. Thank you guys, bye. Now let's continue to the real-world application. It includes, first, personal data protection, storing sensitive information like passwords, PINs, or identification number in a secure manner. Preventing unauthorized access to personal records. Second, secure access control, implementing passcode-based access for devices like safes, lockers, and secure storage systems. Third, educational demonstration, serving as a practical example of integrating hardware and software to create secure systems in educational settings. Fourth, prototyping for IoT devices, acting as a foundation for developing secure IoT devices that require data protection. And then fifth, corporate security systems, implementing similar mechanisms in corporate environments to protect sensitive business information. There are a few lessons I learned from this project. And let me tell you. First is system integration and design flow. The platform designer simplifies the integration of components by providing a graphical interface for system design. It became clear how important it is to carefully configure interfaces, clock domains, and address mapping to ensure proper functionality. And I also learned about the clock management. Handling multiple clock signals is essential for stable system operation. The use of PLLs to generate various clock outputs highlighted the significance of meeting the timing requirements of different components such as SD-RAM and peripherals. I also learned about the address mapping and resource allocation. The need for accurate address mapping was a key takeaway, and a misconfiguration in address ranges for memory or peripherals can result in system malfunctions, demonstrating the importance of careful planning and verification. Fourth, interrupt handling and peripheral communication. The role of interrupts in managing peripherals and ensuring efficient task handling became apparent. Learning how to configure and prioritize interrupts helped me better understand hardware-software interaction. Fifth, signal export and external interfacing. Exporting signals such as clocks, resets, and PIOs for interaction with external hardware, like switches and LEDs, was a critical aspect of the design. This provides valuable insight into connecting internal FPGA logic with the physical world. So, to conclude, the Secure Information Lock project successfully demonstrates the integration of hardware and software to create a secure and functional system. By leveraging FPGA technology and tools like Platform Designer, the project ensures robust protection for sensitive information. The implementation of passcode verification, coupled with user-controlled display mechanisms, highlight the importance of security in modern embedded systems. So, this project not only serves as a learning experience but also paves the way for real-world application in data security and embedded system design. And for the future enhancements could include adding encryption mechanisms, biometric authentication, or remote access capabilities to further strengthen the security measures. So that's it for my embedded system final project. Thank you for listening to me, and bye bye.